All right, yesterday we were talking about even and odd functions, and who wants to summarize real quickly. An even function is a function that it has y-axis symmetry, right? That's your folding symmetry. And a function that is odd has rotational symmetry, or what do we actually call it? Origin symmetry. Good. And the test is, remember, to replace x with negative x. And if you get the exact same thing you started with, then it's what? Even. And if you get the opposite of what you started with, it's odd. Okay. So I showed you how to do the formal argument, but then we had a little summary, right? A function, if you just have terms, a function that is even when you replace x with negative x, if no terms change signs, if they all are preserved like the original, it's going to be even. If all the terms change signs, it's going to be odd, right? So if a function has a constant at the end, can it be an odd function in general? No, because if we need all the signs to change, a constant by definition does not change. That's going to be like a vertical shift on the graph. And it makes sense, because if you have a function that has origin symmetry kind of like this, and you have a vertical shift, if you add a number to it, oops, I'll do it in two parts. There we go. Does that function have origin symmetry anymore? No, if you turn your iPad upside down, the y-intercept is now negative instead of positive. So vertical shifts kind of mess up origin symmetry. Do vertical shifts mess up y-axis symmetry? No, they don't, because we can, oops, that's the wrong thing. We can move those up and down all day long, right? And it doesn't mess up the y-axis symmetry. Does a horizontal shift mess up, thank you. Does a horizontal shift mess up y-axis symmetry? Yes. Okay, very good. Then we were getting to quotients. And if we have a quotient of two functions, we can actually look at the numerator and the denominator separately, right? And we came up with the summary that odd functions kind of act like what type of numbers? Negative numbers, and even functions act like positive numbers. Okay, so let's summarize that down here. For polynomials, this is just for something that is multiple terms. If none of the signs change when you replace x with negative x, then the function is what? Even. And if all of the signs change, then the function is odd. And if some signs change and some stay the same, then the function is neither, even nor odd. Neither. We call it a neither function. All right. Now for quotients or for ratios, an even over even is even. Good. An even over an odd, or bless you, an odd over an even, bless you, is an odd, because that's like a negative over a positive, or positive over a negative is negative. An odd over odd is even, because that's like a negative divided by a negative is a positive. And then, like Kevin recommended yesterday, we can pretend like neither is like zero, the guy you don't want to invite to your party. What'd you bring? Nothing. What are you here for? No reason. Nothing. Zero, right? So what happens if you have a neither over a whatever, or a whatever over a neither? You get a neither function, right? Party pooper. The guy that eats all the chips. Right. Have you seen that commercial for the new rolled Tostitos where they're going in there and the guy calls him like Fred or something, and he takes his rolled Tostitos and eats them all, and then at the end the guy says, "My name's not Fred." That's kind of disrespectful to that guy. Anyway, it helps to have those rules memorized, but it's never, ever an excuse for not knowing how to do the algebraic test. So remember, I'm going to ask you to go through the formal algebraic argument of replacing x with negative x, and then showing me how it works out. You're like something like what we did here on H, at least for this coming test. And then after that, in the future, we're just going to be interested in symmetry as an aid to graphing. Then you should just be able to look at it and tell, hey, it's even or odd or neither. All right, example 7. For each of the following, we're going to use all the knowledge that we've learned this year so far to come up with a sketch of this function without using the calculator. So we're going to be looking at the domain. We're going to be looking at the end behavior. We're going to be finding x-intercepts and y-intercepts. That's kind of a review from Algebra 2. Symmetry is an aid to graphing, because if you know the function's an even function, and you know what it looks like in quadrants 1 and 4, do you have the whole graph? Yeah, just reflect it across the y-axis. All right, here we go. 7a. Bruh. Say what? Yeah, let's find the domain first. It makes sense to find the domain first, because why are we going to be trying to graph this function where it doesn't exist, right? How are we going to find the domain of a function like this? Set that did not, right, not equal to 0. There's no radicals. We know that we can't divide by 0. Very good. So let's do that. So 3x squared plus 9x minus 30 cannot equal 0. This is finding the domain. Very good, very good, very good. And if it's equal to 0 or not equal to 0, we try to factor it. And the first rule of factoring is to Google it? No. Look for a 3. No. Not always look for a 3, but in general, look for a common factor, right? In this case, it's 3. Good, yeah. So we factor it out, and we put it on the outside. We don't just get rid of it. We have x squared plus 3x minus 10. So I'm going to keep the whole thing intact. Now I have a quadratic, and I look for factors of negative 10 that add up to 3. Oh, please exist. Anyone? 5 and 2. What kind of 5? What kind of 2? Negative 3. Negative 2. Positive 5. Wait. Well, we have to have a positive 3, don't we? And so the product that has the larger value needs to be positive. So 5x and a negative 2x. That'll work. Good. So that's it. Now from there, this is still the full intact version of the denominator, sorry. But now we know that x can equal negative 5 and x can equal 2. Those, well, is 3 ever 0? No. Let's see. What is 3 always equal to? 3. Is that ever 0? No. What about at Halloween if it goes dressed as 0? Do the clothes make the man? No. So 3 is never 0. It's only the variables that cause the 0. So now I know that these are not in the domain. Let's go ahead and state that. So D sub f, you're looking at a very, very possible prospective free response question, by the way. I would kind of ask these in isolation. Part A, what's the domain of the function? Show your work. So here we go. We showed the work. D sub f now is the set of all x such that x ain't negative 5 and 2. You can list it like that. Negative 5, comma 2. Has ain't been accepted yet into the modern lexicon, into the dictionary? Is it in there, ain't? I know, like, frenemy is now in there. No, I'm not kidding you. Yeah, they just updated the... That's in there for sure, right? Yeah. Yeah, even though the sound of it is something quite atrocious. Now, these are discontinuities, right? The graph lives to the left and to the right of negative 5, and to the left and to the right of 2. So, I need to determine now what kind of discontinuities they are, right? What kind could they be? Possibly a what or a what? Whole or a VA. How in the world do we determine if they're a whole or a VA? Because that's going to affect it when we graph it. We can factor the top, right? And if we can remove the factor that's causing the 0, it'll be a whole. And if we can't, it's an asymptote. Right. So let's go ahead and try and factor the top too. In fact, here's what I would recommend as your general first step. Factor the top, factor the bottom completely. Okay, so in hindsight now, we already have the bottom factored. If I factor the top, I'm going to pull out a 2. I get x squared minus x minus 2. And the bottom is already done because we've already done that work. So even before you find the domain, if you have a rational function, a ratio of 2 polynomials, probably best to just set out to try and factor it completely. And you're going to get a different version of the function that is going to be very useful for particular purposes. So what does the numerator factor as? X plus 1, x minus 2. Yeah, very good. I think we've got it now, right? So, you ready? X minus 2 divided by x minus 2. They divide out. Good. And so what we're left with is f of x equals 2 times x plus 1 over 3 times x plus 5. And that's what the graph is going to look like everywhere except at x equals 2, where we're going to have a what? Hole. Okay, let's go ahead and say that then. So f has a hole, and you can call it a hole, at the ordered pair 2 comma. How do we find the y value? Or f. F is the name, that's fine. You plug in your 2 to what's left right here, yes? This, in fact, is the part of the function f that you can use for the analysis for the rest of the graph, because the only reason you would need to use the other part with the x minus 2 factor in there is to get the whole. Now, if I plug a 2 back into this purple highlighted part, what do I get? Well, if I plug it in the top, I get 2 plus 1 is 3. 3 times 2 is 6. And the bottom gives me 2 plus 5, which is 10 times 3 is 30. Now, does that simplify? It does. So I would expect you to do that as well. What divides out? A 2 or a 3? A 3 divides out, right? Oh, did I do it wrong? Yeah, okay. Let's try it again. Okay. You're in good company. Yeah, let's wait, Anthony. You and I should not be in charge of this. All right, what do you get when you plug a 2 in the bottom? Someone besides me or Anthony. 2 plus 5 is 7 times 3 is 21. I guess it's 21, Anthony. Oh, so you do it first? Right. Your dear Aunt Sally. Your dear Aunt Sally. Okay, now y'all can help me with this one. 6/21 simplifies to 2/7. Good. All right. 2/7. Now, this is important. It's not a point on a graph because it's a hole, but when we graph it, we're going to put a what at the ordered pair? 2 comma 2/7. An open circle. And it gives us a target through which we can sketch the graph. All right, so that means that the other value that causes 0 in the denominator, namely the -5, that's the location of a what? Vertical asymptote. So let's go ahead and say that. F, or f of x, has a VA at, and you can use the at symbol, x equals. Excellent. If you don't put x equals, guess what? RONG. Wrong. Now that's also going to be important because that's going to affect the graph. We'll draw that first. Whenever you're sketching a graph, you always want to draw your asymptotes first because they become guidelines essentially for the graph. Well, I'm going to come back to the X-Intercepts, but we can find them really in any order. I'll ask them in a specific order on the test. Here's what I'm naturally thinking of now. If I just found a vertical asymptote, what other kind of asymptotes have we looked at? Horizontal. Are horizontal asymptotes discontinuities? No, they describe the what? End behavior. So let's find the end behavior next. That's the limit as x goes to infinity. That's the limit as x goes to negative infinity. That's the notation that we would write. Now, for that, you can look at any version of f of x you want. We have this highlighted purple version, which is great, but notice the original version is expanded. And for the end behavior, it's easier to look at the expanded version, right? Because for huge values of x, what determines the growth for the most part in the top and bottom? The leading term. The leading term, right? And then ultimately then we look at the leading coefficient. So you can kind of neglect everything that's not the leading term. Now, is the leading term always in the front? No, it's the one with the largest exponent. So in this case, if you were to simplify this, they're growing at effectively the same rate, right? X squared over x squared. So that same infinity would divide out, leaving you a what every time? A 2/3, right? There were 3 cases. When the degrees are the same, it's the quotient of the leading coefficients. When the denominator grows faster, like if it had this been x cubed or x to the 4th in the bottom, then it's always what? If the bottom grows faster than the top, your ratios are getting smaller and smaller, approaching 0 every time. If the top had been a larger degree, like x cubed, x to the 4th, now the top's getting bigger. Now your values are going to either infinity or negative infinity, and then you plug in to figure out the sign. But we got 2/3, so the end behavior is 2/3, and it'll be the same on both sides. Now remember the definition of a horizontal asymptote. It says if either one of the end behaviors equals a finite y value, then we have a horizontal asymptote at, well, let's go ahead and say it. So f has a horizontal asymptote at, yes, y equals 2/3 because it's a horizontal line. If you don't put y equals, guess what? Wrong. RONG, very good. So that's another thing that we're going to draw first. We're going to draw a horizontal asymptote at 2/3. All right, let's look at a couple of other things. X-intercepts, y-intercepts. We haven't really looked at x-intercepts this year, but you've had them before. An x-intercept is going to be where the graph crosses the x-axis. And what do you know about the function value on the x-axis? Anywhere on the x-axis, what's the y value? 0. So to find an x-intercept, I'll do that work right here. To find an x-intercept, you want to know where y is equal to 0. Well, for us, our y values are f of x. Now, you got to be careful. If you were to set this version of f of x equal to 0, first of all, a fraction is equal to 0 when the what is 0, the numerator or the denominator? The numerator only. If you just looked at this version right here before we divided out the x minus 2's, what are the two x values that cause a 0 in the numerator? -1 and 2. But is 2 an x-intercept? No, because it not only causes a 0 in the top, it causes a 0 in the bottom. So when you're finding your x-intercepts, you want to look at this version right here after you get rid of any holes. Okay? So for a function that's a ratio, it's going to be f of x is going to equal 0 when you get a 0 over a non-zero. That equals 0. That's important. Non-zero over 0 equals 0. Just to put them all together here, 0 over 0 means what? Whole. And non-zero over 0 means vertical asymptote. So those are kind of the three things that you need to be aware of. All right, so now if I go back down to this one, after I get rid of the whole, what's the only x value that causes a 0 in the numerator? -1. That's the only one. So that is the only x-intercept. And so when it's factored, it's easy to do that. Well, don't do that. So we have an x-intercept at, you could say x equals -1, or if you want to write it as an ordered pair, that's fine too. We're going to plot a point at -1, 0. It's the only x-intercept. Now those are generally the harder of the two intercepts to find. But if it's factorable, you're staring at your answer when you have the factored form, again, after you get rid of the holes. If you ever call a hole an x-intercept, you're going to lose points, right? Because it's not. All right, now the y-intercepts, those are generally easier to find. How do we find y-intercepts? If you're on the y-axis, the y value can vary, but x is equal to 0. Yeah, and those are pretty easy to find. That's just going to be f of 0. When you put f of 0, you're telling me that you're finding a y-intercept. When you say f of x equals 0, you're telling me you're finding a 0 or an x-intercept. So the notation is important. You have to communicate your results. Now, how do we find f of 0? You could plug it into any version you want. You could plug it into this version here. What do you get when you plug in a 0 here? I don't know. Yeah, I mean, you and I probably shouldn't be doing it, right? You get 2 over 15, 2/15. Yeah, that's redemption. We get it. Or you could plug it into here, right? The expanded version is kind of nice for the x-intercept or the y-intercept because when you plug in a 0 for x, what happens to every term that has an x in it? It goes away, and you're just left with -4, -30ths, which of course simplifies to 2/15. So it doesn't matter which one you plug into ultimately. You know, just choose whichever one you want. So that's 2/15. So we have a y-intercept at 2/15. You could say it like that. Or, of course, you can list it as an ordered pair, 0, 2/15. So what that means now is we have another point on our graph. We have 2 points that our graph has to pass through, and really if you count the whole, we have another location that we have to hit with our graph from either side. How many points does this graph have, though? A lot, infinitely many. So we have essentially 3 locations out of infinity. So that's pretty good. That's a good start. Now we need symmetry. That's about the only thing left to find. So let's just do it without the argument. This is the case where I'm not going to make you, like, give me the formal argument. Let's look at the numerator. Is the numerator even, odd, or neither? This one's an even, so the sign will not change. This one is an odd exponent, so the sign will change. Yeah, I got a neither. Now, does it even matter what the denominator is? No, it's whatever. But kicks and giggles are fun. So what is the denominator? Even, odd, or neither? It's also neither. Now, is a neither over neither something? It is something. It's still neither, though, right? So this one has no symmetry. Well, we don't have a jump, do we? A hole. Very good. We could still have a hole and have symmetry. If our hole is on the y-axis, we could still have y-axis symmetry. If the hole is not on the y-axis, we would need to have 2 holes, wouldn't we? For y-axis symmetry, we would need to have symmetric holes on either side, or for an odd function, we would need to have 2 holes. So yeah, if you notice right away, the hole is at 2,2/7. There's only one. That's not on the y-axis, so it's not going to happen. All right, let's sketch the graph now. Everything that we know. Right, only one. Draw your horizontal asymptote at y equals 2/3. Right there. Draw your asymptotes first. We have a vertical asymptote at -5. That's right here. There you go. Now the intercepts are easy to put. We have an intercept at 0, 2/15. Now where is 2/15 compared to 2/3? Above or below? It's below. And we have an x-intercept at -1, which is right there. There's no symmetry. We have a hole where? We have a hole at 2,2/7. So that should be about right there. And I think we're ready to go. Notice that the asymptotes kind of define the shape. It's like gravity. So there's only one way the graph can look like. It's going to come from -infinity. It's going to pass through that point, It's going to hit the hole, and it's going to approach 2/3 apparently from underneath. And that's it. It can't live above the horizontal asymptote because then it wouldn't be a function. Now notice to the left, I have 2 options. My graph can either live up here above the horizontal asymptote or below. How do we know where it lives, above or below? It can only live above or below on either side. And since we had all this evidence on the right side of the vertical asymptote that it lived below the horizontal asymptote, it has to be above. Why? Very good. If it lived on the bottom, we would have found another what? X-intercept. Did we find another X-intercept there? No. So by process of elimination, it has to live above. There you go. That's what the graph looks like. And then from there, we could figure out the range. What's the range of this function? Ranges are a lot easier to get from the graph. A set of all y such that y does not equal 2/3. That's the horizontal asymptote. And there's one other y value we don't hit. The y value of the whole, which is 2/7. All right, we will finish up on Monday and then look at PSAT the rest of the week through Wednesday. We'll review on Thursday through section 2-3. We'll test Friday. The worksheet is not going to be due Monday. No, we didn't finish. So the worksheet is going to be due on Tuesday. Y'all have a good weekend.